All right, so as you can see, you've got a bunch of, I don't know if you can read what numbers those are, but 4.1, 4.2, 4.3 homework is all due tonight. So we've talked about most of that pretty thoroughly. What we're going to spend some more time on today is the 4.3 with a little bit just more analysis, like investigation of how the functions we're talking about now are different from the ones that we were dealing with in large part prior to your test, the linear functions. So linear functions, constant rate of change functions, those indicated from one value of the input to the next, we increase by a fixed amount all the time. But it's not just between one and the next. It doesn't have to be 1 unit apart. It can be any number of units apart. If you compare the change in output to change in input, you get the same quotient. Change in y over change in x, that slope is the same between any 2 points, not just 1 point and the one next to it. So like 70 miles an hour doesn't always have to be like 1 hour increments. They can be like, you can talk about 7 hours or 2.6 hours or whatever, but it's always that ratio of 70 miles for each hour, no matter how many hours that might have been. So exponential functions is what we're dealing with now. Exponential functions, the term comes from the fact, like linear has to do with a line. If you graph it, that's what it looks like. Exponential, it doesn't look like any exponent when you graph it. That comes from the fact that in order to create these functions, we multiply repeatedly, where the number of times we multiply, which would be repeated multiplication with varying exponents, determines how far we go on a graph or how much later we're going. The exponent is the input variable. How many times am I going to increase by this 3%? 5 years, 7 years, or whatever the time frame might be, something like that. 2.72 years. It doesn't even have to be whole numbers in a lot of cases. Now, some of the examples we're using only really make sense for integer numbers as those exponents. We'll talk about that, but let me get you something. This is just something that you can write on that's related to an example we talked about in class on Tuesday. The 2 phones, and one was decreasing in value by $45 a year. One was decreasing in value but by a percentage. So that 1 year over the next, the later year was a 30% decrease from the previous year. Meaning, alternatively said, 1 year's value is precisely 70% of the years before. And it was just phrased in terms of whole numbers of years. Maybe it applies also to half a year or something. Don't know. Let's just talk about the whole numbers for right now. And I want to do some comparing between those two, just to make sure we understand the relationship between the two sorts of change, what their graph looks like, but also some computations that we've done or can do, and how they work out differently for these two sorts of functions. So I have a copy of this also someplace. Here we go. So take a look at this. We've got, I'm asking for the same general computations. The one on the left was what was the name of it? iTech. The iTech phone, the one that was a 30% decrease per year. And there's 6 different computations to do there. The one on the right is the Dynasystems device. I guess it wasn't phone, it was some sort of device. Those decreasing in value by $45 per year. So sometimes those are, similar to one another in terms of what those values are. Sometimes they're not, but the pattern isn't described the same way. So what you can do in terms of computing these values, just take a look at a few of them. At least write out what the expression would be. We'll talk about the values if you don't get all the way to computing. But there are 2 different sorts of computations, as you see. A quotient of some values. Some are consecutive values, like 1 year apart. Some are not. And then there's some difference quotients, where it's not just a quotient or comparison, but a comparison of the differences. A couple each of those. One for 1 year apart and one for not. So one thing you can think about looking at these is the fact that some of them have the same values. Even if finding that value is tedious in certain cases, some of them might have the same values. In fact, on the left example, the 30% decrease per year example, let's see, precisely 2 of those have the same value as one another, of those 6 expressions. Actually, same for the one on the right. Exactly 2 of them have the same value as one another. So in the first example, the exponential relationship, that curved graph, where we've got a percentage decrease per year, what's the value of this first expression? F of 1 divided by f of 0, meaning the y values in quotient. If I were to reduce that, what does it come out to? Should be a nice decimal. Thoughts? 0.7. Okay. Sounds good to me. That would be 210 divided by 300, otherwise known as 21 over 30 or 7/10. 0.7. What about f of 4 over f of 3? That would be 72.03 divided by 102.9. Doesn't look very pleasant, but it does come out to actually a nice number. These are rounded, but you can probably guess what that quotient comes out to. Thoughts? Well, yeah. Yeah, it's 0.7 also. Actually, what I'm going to do, save a little space here. There we go. Those are both 0.7. 0.7 is a special number with respect to this question. It's a 30% decrease in value per year for this device. And if you saw at the bottom, I just kind of put this on there. This was on the, what was it, Module 4, Investigation 1. Just to highlight the whole number values here. That first one, 300 versus this 210. That shrank quite a bit, but the ratio of those two, this value, this y value 210 compared to that value of 300, that was at 210 divided by 300, 70%, right? 0.7 as a decimal when we did that division. That's precisely what that 30% decrease means. And what I mean by how this means that at all, if I take this value of 300, if I find 70% of it, or 30% of it, the dividing point, 70% and 30%, those complementary percentages again, those are the two parts to this. If I lose 30%, this portion up here, what remains is 70% of the original value, or the difference in heights between these two lines is the 30% of the height of the first one. Or the height of the second line is 70% of the height of the first one. So 70%'s there, 30%'s missing. But that's true for each of these consecutive lines. So what was it, 3 and 4? Is that what I'd asked about? Yeah, 3 and 4. The height of line 3 versus the height of line 4. The value after 3 years versus the value after 4 years. Still 1 year apart. So the amount that it shrank is a lot less in terms of number of dollars. But if this relationship is a decrease by 30% each year, then from this price, this height here, which is just over $100, if I lose 30%, I'm keeping 70%. 70% is the height of this, 30% is the difference in the height. And those percentages are both relative to the earlier number, relative to the value after 3 years. So the ratio between height of line 4 and height of line 3 is 0.7 to 1, or 70%. The later one's 70% of the earlier one. And that's true for any two consecutive heights here. If I picked year 6 and year 5, 5 and 4, 4 and 3, 3 and 2, any pair of consecutive heights, the ratio of them would be 0.7, or the later one's 70% the height of the earlier one. The difference in height is 30%. It's shrinking by 30%, but what remains is 70% of the original. So that's why these two both have the same value here. Let's see if I can click someplace else. Because those are both talking about consecutive years. Now, if I were to look at year 2 compared to year 0, is that 60%? Because it says 30% per year. Yeah, 0.49. It's not. Yeah, it's not a 60% loss. It's less than that. If you remember what we talked about when we were doing these functions as 30% per year, it's not 30% of the starting number every year. It's 30% decrease from 1 year to the next. And then at the beginning of the next year, we use that value to figure out, well, how much is this 30%? So it's 30% of an ever-changing number, even if we're just looking at whole numbers of years, which maybe makes sense in terms of how they mean selling these devices. Maybe it doesn't. But to find this decrease, I did 30% of 300 and subtracted it, or found 70% of 300. But then to get this next value at f of 2, to find that value, I can think about starting from this 210 and finding 70% of that. Now, that's not a very efficient way to calculate these values. We talked about how to just calculate so many values into the future. It's repeated multiplication by 0.7. Because of how order of operations works, I can do stuff like, well, if I take the f of 0 value and I multiply it by 0.7, I get f of 1. And so if I take that result and multiply it by 0.7, oops, typo, there we go, I get year 2's value. I don't really need those parentheses, though, because it's all multiplication, right? All we're doing is multiplication. And multiplication, if you switch around the order or do some pieces first or other pieces first, that's just your own preference. And if we're thinking about doing this in order starting from the beginning, I'd say first find f of 0 times 0.7, find 70% of it, and then find 70% of that answer. But since it is actually all multiplication, I don't need those parentheses for anything. I can multiply any of those three things. Let me put in the leading zeros just because decimals hide from a distance. There we go. I can multiply any of those that I want first. And so I could write this, instead of writing multiplication by 0.7 twice, I can say multiply by 0.7 squared. Even if they say, oh, well, that's 0.7 multiplied together first and then times f of 0, that's fine. Same result. It's the same three things multiplied together. So if I want to compare f of 2 and f of 0, then, if f of 2 is this, f of 0 multiplied by 0.7 a couple of times, and f of 0 is obviously just the f of 0 part of that. If I put those in a fraction together, you can see what it reduces to. Even it's not a very nice number if you do the division. 147 divided by 300, it's at 0.49, or what have we had? It's definitely not 0.4 or 0.7 or something like that. It's a different number. But what it is, and maybe you can see from here, it's exactly 0.49. Because I'd have to write f of 2 divided by f of 0. I'd have, and let me see if I can get my equation things back up. Oops. There we go. So I can get myself a fraction here. F of 2 is the same as f of 0 times 0.7 squared. Or I'll just do times 0.7 and times 0.7. And f of 0, well, is f of 0. And those two can cancel out, so I've just got 0.7 squared. And so instead of writing this big ugly fraction, I'm just going to write 0.7 squared, which, oops, I don't want that. I wanted to delete that. Sorry, I hate this equation editor. 0.7 squared. So 1 unit apart, the first two, that ratio came out to be 0.7. 2 units apart came out to be 0.7 squared. What about f of 2 to f of 5, or the ratio f of 5 over f of 2? Guesses on how I could write this without grabbing a calculator? Well, yeah.
Would it be 0.7 to the third?
Absolutely, because that's 3 units later. So if I were to write out f of 5, I could write out f of 0 times 0.7, 0.7, 0.7, 5 times, and f of 2 in the denominator would be that starting value, f of 0 times 0.7 times 0.7. A lot of those 0.7s cancel out, definitely the f of 0s cancel out. The top has 3 more factors of 0.7 in it, of 70%, than the denominator does. So let me just save myself some hassle here, maybe. I'd have 0.7 cubed. I don't know what that comes out to as a nice number, like 20-something percent, 0.2 something, 0.3? 0.34. Yeah, not particularly nice numbers written out as decimals, but in terms of their overall value, let me just move this over here. In terms of their overall value, in terms of, like, if you were working through this to calculate them out, the pieces involved in their computation, you can reduce without doing the computation. So we can see this pattern that we've got here with exponential functions, functions that rely on a percent change or a multiplicative change from one value to the next to the next. I can use, whatever that percent is. So, well, 30% decrease, we're keeping the 0.7 as we talked about. But after 2 iterations, so 2 units later from wherever we're starting, whether it's at the beginning, 0 or 3 or 17 or whatever it might be, if I'm going 2 units later, I'm going to use that multiplication twice extra. So the ratio of change is going to be that factor multiplied on twice more, so raised to a power of 2. Or for 3 units later, we would have to use that factor 3 times. For 7 units later, I'd have to use that factor 7 more times. So without doing the ugly decimal math here, we can find out what the ratio should be based on the structure of the function. Now, and what I mean by it's not just, it doesn't have to start at 0. These two, I happen to start at f of 0, the original value here, and not there. They both have that same ratio of 70%. The later one's 70% of the earlier one. Sometimes we use 0 at the beginning, sometimes not. Doesn't matter. Doesn't matter where this initial part or what the point of comparison is. It's just what sort of function do we have? How much later have we gone? So looking at the same sorts of things in the linear function, g of 1 divided by g of 0, 255 over 300. I'm sure that reduces by something. It's in fact multiples of 5, but thinking about dividing g of 4 and g of 3, 120 over 165, or g of 5 over g of 2, 75 over 210, none of those are the same, and they're also not related to any computations we do in putting together a linear function. Doing this division of the y values themselves doesn't help us find the values. It's not related to this $45. You can divide any of these you want. I don't think there's any, I'm sure there's one combination of numbers that are on that line where the y values divided and come out to 45, just because there has to be some numbers that are a ratio of 45 someplace on there. But it doesn't have anything to do with how we compute this $45 decrease per year. That $45 would be like a negative something. It's not like we do a comparison and it's really some 55 instead of 45 based around 100. There's no trick like that. There's certainly not any negatives going to come up from dividing things here, unless we do some subtraction. And as you remember from generally working with linear functions for quite a bit of time in your earlier life, I'm sure, when you're trying to find, when you subtract values like this, change in y over change in x, that is precisely how you get slope from something that you don't know. In this case, it relates to this rate of change or the decrease in the phone's value per year. If you do these, change in y over change in x, corresponding points, y2 minus y1 over x2 minus x1, whatever symbols you want to imagine, these are all going to come out to be equal to one another. And they all come out to be negative 45, regardless of how far apart the points are, regardless of where on the line, where in time, context speaking, we're talking about. If I pick any 2 points that are on that graph, if I pick the value of the phone at any 2 points in time, and I do these sorts of subtractions, it's always going to come out to be this negative 45, which indicates that decrease of $45 per year. The numerator here is dollars, the denominator is years. Now, we didn't talk about units here. When we were dividing y value divided by y value, it's the same units in the top and the bottom. That's why we didn't have, like the units cancel out. So we get this number that's just a decimal in these cases, just a numerical result with no units remaining. That seems kind of strange. Now you could actually think, oh, well, it's really just comparing the same units. I don't have to get rid of them. F of 1 compared to f of 0 here is, what are the numbers? $300 compared to $210. So the later one is, 70% of the dollars of the earlier number of dollars. You could, explain it in terms of dollars that way. But that's why we weren't really concerned about the units, because it's the same units top and bottom. And so it's just this comparison of the size of those two of the same things, size of dollars compared to another size of dollars. On the other hand, when we do this subtraction, I've got dollars on the top and years on the bottom. This is negative 45. That'd be dollars per year. And let me just scoot this over. There we go. So I know it always comes out to be that same number. That's how this function was set up. That was the meaning of it. That visually it looks like a straight line, but the meaning of that is that for any 2 corresponding points to any corresponding times with dollar amounts, there's the same amount of decrease in y, decrease in value, for a corresponding amount of time that's passed. And it's $45 per year, whether it's 1 year, 2.7 years, 5 years, and no matter which years we're talking about. If you can see from this graph here, that subtraction, division, difference quotient computation is not going to come out the same all the time, right? If I were to find, what was that first, f of 1 and f of 0 divided by 1 minus 0, that'd be the slope between a straight line connecting those first 2 points that are highlighted. Now, it looks kind of like a straight line if you only look at that section. So in reality, between those first 2 points, I could estimate what's going on between year 0 and year 1 pretty closely with a straight line. But if I were to try to estimate between year 1 and year 2, I'd probably pick a different straight line, because this is getting less and less steep as I go down. I know it's actually curved. That's how it's drawn, is a curve. It's not actually straight line segments connecting dots. But I can say like, well, that looks pretty straight. So it's got a negative slope of something, but this is a negative slope of something else approximately. Or if I were to straight line connect the 2 points at the ends of each of these intervals, they would certainly be not all the same steepness, right? So whatever one of them comes out to, another one's probably not. You could, by coincidence, pick some points that are differing, like 0 to 4 might be pretty close to 2 to 3 if I look at the slopes between over 2 different intervals, one inside the other. But that would just be by coincidence, not because of how this is set up. But these then, I say, well, whatever this first one is dollars per year during the first year, and dollars per year on average rate of change between years 2 and 5. I could find those things, but they're not going to be the same for every set of points here, and they're really going to be tedious, so I don't actually want to go through computing them. But just in terms of the graph that I'd had at the bottom of that sheet that I gave you, I just wanted to point out again, you'll see some of these kind of interspersed with regular looking graphs throughout the homework. The point of this is to help, instead of focusing on how one point is connected to the next, just to focus on this, on a sequence of values, especially when maybe it's just the whole number values that are important. It's okay to see that curve pattern or straight line pattern, but just if you can see, like in this first one dot, the height of it is 70% the height of the one before it. This height is 70% of the one before the one at time 1, and so on and so on. But with these, it's not finding a percentage. It's just always, oh, lower by 45, lower by 45, lower by 45, lower by 45. So each consecutive vertical line where the height of it indicates a value of the phone after however many years down at the bottom, each one's 45 units shorter than the last one, as opposed to in the first graph, each one is 70% of the height of, or is 30% shorter than the one before it. All right, so in any case, you'll see these graphs like that. It's not something I'm going to ask you to recreate, but if that helps you visualize or just focus on the y values as opposed to the sequence of events with all the curves in between, these are maybe kind of helpful in seeing that. I think it's very useful with the percentages. So you can say, oh, 70%, and you can kind of visualize where that is, or 75%, 50%, and you can imagine cutting these in half. All right, so let's see. There's something else I wanted to show you next. Oh, I know. We left off the end of class on Tuesday. I had it's kind of like a worksheet. But we went through these annual raises and monthly price cuts, and then I said, compound interest, we'll talk about that next time. Now is next time. So this function, or this worksheet was about how do you write an expression to model these exponential relationships. So using that repeated multiplication. And the first one we talked about, okay, so starting salary of $30,000, and you get a 4% raise annually. You're going to take 30,000 and multiply by 1.04 to get all the original back plus an extra 4% to get 1 year later. To get 2 years later, you'd multiply by 1.04 again and again and again. So we came up with functions like, let's see, 30,000 times 1.04 to the x. So salary x years later, I'd multiply on 1.04 x different times. And we could evaluate it after 5 years. For the monthly price cuts on the cell phone, we started at $700, just reviewing what we did already. Started at $700, and there's a 2% price cut per month. So, let's see, let me just put in my silly equation editor here. So I wanted to write an equation, apparently I need to be verified. But starting at $700, the price is reduced by 2% relative to its price during the previous month. What is it that we multiply to make a decrease of 2%?
0.02.
Not quite. Let's see, if I multiply by that, I'm going to get the 2%, but I want to decrease by 2%. What's the other number? Yeah?
Would it just be negative 1.02?
Almost. I can throw one more thing in here and it'll take care of everything.
0.98.
Yeah, I want a 0.98, or I want this for after 1 year. I'd take all of my 700 and subtract 2% of it. So if I'm taking off 2%, I need to find 2% and subtract it, which I could write like this, or instead of writing 1 minus 0.02, I use that complementary percentage, 0.98. So just like in the previous question we were talking about with the cell phone values, it was a 30% price or value decrease over per year, and we multiplied by 0.7. So 0.7 is what remains, 30%, 0.3 is what was gone. Here, 2% is gone after a month, so that means I'm keeping 98% from 1 month to the next, or a later month's value, or price, selling price here, a later month's selling price is 98% of the previous month's price, because it's decreased by 2%. So it's not all of it, it's 2% less than all of it. So this would be after 1 month. If I want to talk about after m months, then I need to raise this to the m power. And then I'll call it a function. So does it say what to call it? No. F of m. Now it's a function. So something like this tells me the value after m months have passed. If I put in 0, notice, 0 is an exponent. Anything raised to the 0 power, well, other than 0 to the 0 power, anything raised to the 0 power is equal to 1, meaning I haven't multiplied on any factors of 0.98. I've just left it as 700 by itself. So when m is 0, this has a value of 700. When m is 1, I've multiplied by 0.98 once. So that gives me the value after 1 month. When m is 2, it would multiply on that 0.98 yet again to the previous result. So times 0.98 twice, not 0.98 times 2, but 0.98, 0.98, multiplied on twice. So if I wanted to find this purchase price, is not going to be pleasant, but I would just substitute in 6 for the m, 6 for the exponent. Now, compound interest here. You might have dealt with compound interest and weird formulas and stuff in some class previous, whether college algebra, algebra 2, something like that, whatever it might be called. But it's not really a special formula. It's just got specialized terminology that bankers use. That's the only specialness to it. It's just an exponential, in the case of earning interest, exponential growth formula. So more similar to the first question here, where we started with a salary of $30,000 and we increased by 4% per year. Let me do this with my, no, this one, sorry. Insert weird equation. I'll say f of x, just to call it something. F is 30,000 times 1.04, all of the original with an extra 4%, multiplied on a number of times that indicates the number of years that have gone by. So after 2 years, I'd be multiplying by 1.04 twice, etc. So our compound interest, as we're earning something, not decreasing, it'll be more like this one in that our growth factor and this 1.04 here, the 0.98 here, those are both referred to as growth factors, even though when it's less than 1, it's actually talking about a decrease. It's a general term because they didn't like change factor, but that's the factor that we multiply by to get from one unit to the next, no matter where they are. It can be whole numbers, it could be from 2.5 to 3.5, but it's a 1 unit percentage change is what it tells us. Well, it tells us about the percent change. We have to do a little interpreting. But in this case, it says we've got an investment account that pays 3% annual interest compounded quarterly, which means that every quarter of a year, your bank pays you 0.75% interest. That's the bank terminology. This 3% annual interest compounded quarterly just means you get 0.75% 4 times a year, so that over a year those numbers add up to 3. That's bank stuff. But if we start with $20,000 and I know how much my value is growing, we can use the same patterns to write functions for this. Let me just call it, I'll call it something else, V. The value after Q quarters have gone by. Well, we started with $20,000. And we're growing by a little bit, 0.75%. Well, 3/4 as a number is 0.75, but if I put it in 0.75, that's 75%. When I had 4% in the earlier question, that 4% increase led us to that 1.04 growth factor, because we have all the original plus 0.04, which represents 4%. So if I want 0.75%, it's going to be 1 point something, but I need the decimal form of 0.75%, slightly less than 1%.
Isn't it like 0.75?
What was that?
Isn't it 0.75?
This would be 75% increase. So like this is 4%.
Okay.
So not quite, but almost.
So do you take the 3/4 from the 0.04?
Yeah, so 3/4 as a number
Okay.
is 0.75, right? So I want 0.75%. Add 2 zeros. Yeah, 4% is 0.04. 0.75% is kind of weird. Means the same exact thing as 0.75%. I need to make a small number. This is slightly less than 1%. 1% would be a 1 here, so I need something smaller than that by a little bit. It's this, that lovely number. So moving the decimal twice, 4% means 4 divided by 100, or 4/100ths. 0.75% means 0.75 out of 100, or move the decimal twice, 0.0075. So very small percentages are weird looking, but this is almost 1%. If there had been a 1 here, just a slightly larger number, that'd be 1%. So this is 0.75%, and again, I don't have to write it with the plus, I can write it by adding 1 to a decimal without a number in front. That's pretty easy. 1.0075. All right, so that's my growth factor. Very small amount of growth, but then again, it was 0.75%. 1 plus 0.0075. And then it increases by that amount, that 0.75% every quarter of a year. So I want this to be raised to the power Q. So here's a function, shows my value after Q quarters have gone by. A quarter just means, again, bank terms. 1 quarter for financial term is a quarter of a year, so 3 months. So if I wanted to find the value of this account after 8 years have gone by, what would be Q? Yes.
8 times 4, so I can't remember what it is. off the top of my head.
8 times 4 sounds good. We can even just write it as that, right?
36? Wait, 32.
Right, yep.
Is it 30?
32, you're right. Yeah, not the most important part of this. The important part is think about what the value is and how do I compute that. Well, how many quarters have gone by in 8 years? Well, there's 4 per year for 8 years. So that's 32 quarters. And if I evaluate that, I'd find the value of my account that earns a little bit of interest every quarter after that long. Because every quarter, and just the meaning of the word compound interest, all that means is that you earn interest every so often, and that affects how much interest you earn the next time you get interest. Kind of like your salary increasing by 4% per year. It's not 4% of your starting salary all the time. It's 4% of 1 year's salary becomes your next year's salaries extra. So in this case, the amount of money that you have in your account at the beginning is that $20,000. But that only determines how much interest you're going to have by the end of that first quarter. After that first quarter's gone by, you have slightly more money, $20,000 plus an extra 0.75%, which is like $150, I think. So if you have $20,150, when you go to earn interest the next time, you get a little bit more because you already earn interest. Your interest earns its own interest. That's what's meant by compounding. The fact that you already got some interest makes you earn more interest, and that's a good thing. If you owe money, however, that's a bad thing. But if you're earning interest, we'll say it's a good thing. So in any case, compound interest is just an example that's a little bit messy of the same exponential growth, but the only reason it's messy is because of banker terminology, financial world terminology. It's really talking about the same stuff. They just word it strangely to make it sound like it's a completely different situation. It's not. We have a certain amount of percentage growth from time period to time period, which are weirdly disguised things. And numbers of times we get interest aren't always per year, even though they usually advertise interest rates on a per year basis. In any case, I just wanted to point that out. Writing these functions, we need to determine a growth factor or decay factor, if you want to call it that, but a change factor, a percentage that's either larger than or smaller than, or a multiple of. It doesn't have to even be stated as a percentage. It could be like it triples every year or something like that. Like, oh, okay, well that's times 3. I don't need to know what percent that is. I'm just going to times 3. So in any case, I did want to talk about that because that was kind of the more challenging problem at the bottom of the worksheet that we talked about last time. Now, last thing I wanted to talk about today is Module 4, Investigation 3. So I'm just going to skip by some of the first couple of questions, but I did want to point out a little bit about this, like I just mentioned. This is a scenario where we're putting 1 penny on the first square of a chessboard and then 2 on the next and then doubling each time. So not 1, 2, 3, 4, but 1, 2, 4, 8, 16. The number of pennies from one square to the next, we're always multiplying by 2 to get that number of pennies on there. So if I wanted to know how many pennies are on the last square in the chessboard, I don't have to work out all the numbers in between. I just need to know, well, I started with 1 and I multiplied by 2 a whole bunch of times. And then figure out how many that is, and that would give you an expression. 1 times 2 to the something power. Now I could state that in terms of percent, and if you want to think of it like this, like, well, how would I get a 2 out of that? It'd be 1 plus 1. So it's a 100% increase from one square to the next. 1 as a decimal represents 100%, but we don't need to convert it into percents. As long as you know what to multiply by, you can interpret it as a percent or not. So something like this, 2 to the x looks very boring, but thinking about those pennies, the 1 times 2 raised to some power, whatever that power might be, could be the number of pennies on the some number of chess square, and in fact it'd be exactly like this. With the chess square thing, I'd only be concerned about whole numbers of x. This graph shows me not just whole number of x values, but all the in-betweens also. And so unlike maybe the cell phone values are kind of like, well, maybe in between years I have an in-between value, maybe not. But just a graph like this, y equals 2 to the x or f of x equals 2 to the x graphed. This is an exponential function also, and this one demonstrates all those values in between. But just thinking about the values on this, I know that based on what we're just talking about, to get from one whole number value of x to the next, I'd multiply by 2. Whether from the second chess square to the third chess square, or the 4th to the 5th, the 19th to the 20th, whatever it is, I multiply by 2 to get the next number of pennies on the chessboard. But that also would be true on here, and it's not just whole number values also, but if I were to look at 2.5 to 3.5, that's 1 unit apart. So regardless of the fact that maybe I don't know what 2 to the 2.5 power is, or 2 to the 3.5 power is, I know they're 1 unit apart, so it should be 1 factor of 2 greater. And if you remember your exponent properties, if I were to compare something like f of 3.5 to f of 2.5, meaning 2 to the 3.5 power minus 2 to the 2.5 power, since our formula is that. If you remember your exponent properties, you subtract the exponents when you're dividing if you have the same base. The top exponent's 1 greater than the bottom. So we get a result of 2. Again, they're 1 unit apart, which means as a multiplication problem, these are in a ratio of 2 to 1. Or the second result is 2 times as large as the first, even if I don't know what either value is off the top of my head. Like 2 squared is easy enough to find. 2 to the 2.5, meh, something larger than 2 squared and smaller than 2 cubed, right? In fact, reminder point here, if I say 2 to the 0.5 power, a 0.5 power means the same as some other phrase we use. What other term do we use for a 0.5 power or a 1/2 power? Square root, right? Yeah, a 0.5 power is the same as a square root. And that seems kind of weird, but if you think about, again, square root of a number is something you can multiply by itself and it comes out to be. So the square root of 2 times square root of 2 is 2. Square root of 2 is some weird number, 1.4 something. But it's the number that if I multiply by itself, it makes 2. Square root of 2 squared is 2. Square root and squared you can also think of as like inverse operations. A square root of something and a squaring something. One undoes the other. Similarly, if I were to write these with 1/2 or 0.5 powers, 2 to the 1/2 and 2 to the 1/2, I could think about exponent properties here. If you have the same base, you get to add the exponents. Or if I were thinking of it as 2 to the 1/2 squared, different exponent property. If you raise something with an exponent to another power, those two different powers you multiply together, and 2 times 1/2 is 1. They all work together, but square root and 1/2 power work the same way in their different systems of writing the same meaning. So they have the same results, therefore they must have the same values. Or that's how we determine that this 1/2 power can be an alternate way to write square root because it has the same properties in terms of how it's related to 2 or anything else. So in any case, if I have something like 2 to the 2.5 power, That's 2 squared with an extra factor of square root of 2 thrown on there. So in any case, what I really wanted to talk about on this, let's see. Here we go. Oh, I was going to say it's something nearby. This 1 unit growth factor. I'm just going to make this a little bit bigger. So this 1 unit growth factor is what we've been talking about as we were talking about looking at f of 2 versus f of 1 or something like this that are 1 unit apart, the output values. Even if I don't know what the growth factor is, if I have a table of values or if I have a graph where I can read some values off of it, if I'm trying to reconstruct a function that I want to be exponential, thinking like, this is probably exponential growth or exponential decrease or percent change. I can find that by I can find what that percent change is or check to see if it does fit that pattern if I have a whole bunch of values by comparing and finding the quotient of 2 consecutive, meaning like 1 unit apart, y values. So f of 3 divided by f of 2 or f of 7 divided by f of 6. If I have a whole table of values and I do that division and it keeps coming out to be the same result, or at least close enough that it could have just been rounding, then I say, oh, well, this fits an exponential pattern or there's percent change pattern. And the result that I'm getting is that growth factor, 1 unit growth factor, if you're taking things that are 1 unit apart. So if you're trying to make a function based on knowing just a couple of values and say, well, here's a couple of values. Suppose that there is an exponential relationship or a percent change relationship. Write a function that goes with these. Kind of like if you have a couple of points, it says, write an equation of a line that goes through these points. Well, this is not a line, but writing something else. So, for instance, taking a look at some messy numbers, here's one where we're given a percentage. Total number of COVID cases in New York increased by 76% each day between March 16th and March 20th of 2020. There were 975 cases at the beginning of that, March 16th. So thinking about writing a function to model the COVID cases is what we're doing here. And so this is kind of a step-by-step. And I'll let you take a couple minutes here, but by what factor do you multiply 975 to find the number of cases after 1 day? Or then by the 20th, which would be after 4 days. And then determine it, like suppose it continues, how would I write the number of cases in general for a while in terms of the number of days past the 16th? And there's a couple other questions. Part 3 is a little messy. But take a minute, see if you can write out what I'd need to multiply by and what would be a function to model this if it continued for a while, long enough to bother modeling it. So increase by 76%. Yeah.
If this is an exponential factor, do you throw the exponent on those, so 76% becomes like 1.76? Would you throw the exponent on the 1.76 and keep the principal number and it was still?
Yep.
Okay.
Yeah, absolutely. Yeah. So I don't know if you heard what that was, but so if we're modeling this with an exponential function or percent change, percent growth or decrease sort of description, then yeah, we're going to have an exponent thrown on the percent part of that. Now, it's not just 76%. It's not just 0.76. But yeah, we're going to have our, what was the number of getting? 975, sorry. So it was 975 people on one day. If I want to find how many, if it increases 76% per day, if I want to know the amount on the next day after this, what is it that we would need to multiply by? Yeah.
1.76.
Right, 1.76. And you can think of that in maybe 2 steps, or a few steps. Because I want to keep all of the original plus an extra 76%, so it's 1.76. Or not quite doubling from one day to the next. Not quite times 2, like the chessboard. A little bit less than times 2. It's not a 100% increase. It's a 76% increase. But this would be after one day. If I wanted to find it after a second day, I could think about know this number and then make that result increase by 76% again, or multiply by another 1.76, and then another 1.76 for the 3rd day, 4th day, 5th day. So it's the 1.76 that we're going to multiply by more than one time if we're talking about more than one day into the future. We don't need to use the 975 times that over and over. It's just the growth factor, just the 1.76 indicating all the original plus an extra 76% as the number of people that are infected by day 2. And then day 3 and then day 4, we need more factors of 1.76 or multiply this 1.76 on more and more times. So just, call it something. Did it give us a letter? F, I suppose. So f of x our function that we could use to model this would be this: we have a starting value or an initial value, and it doesn't mean at the beginning of time, just whatever's the start relative to this was apparently March 16th of 2020. So initial value, March 16th, 2020, multiply by 1.76 as many times as we need, where this exponent tells us how many days after March 16th we're looking to get. So if I put in a 0 there, I would get back as a result 0 days after or on March 16th. So the 0 power would give us just back that 975. After 1 day, after 2 days, after 3 days, that would be 1, 2, and 3 in that exponent position, or whatever number we need. So what about f of 7? What day is that talking about? This question, C2. Evaluate f of 7 and explain what it means. Just what does it mean? Yeah.
7 days after March 16th.
Right, 7 days after March 16th, so I don't know, whatever that is, March 23rd, a week later. So thinking of that, it's a week. A week's a nice time unit. So what if I said, all right, let's find out 4 weeks after March 16th, how many COVID cases there are. I want 4 weeks after. Say, oh, well, just kind of like the compound interest thing, talking about how many years when we were talking about quarters to start with. Just a little time frame consideration to think carefully about what you're putting in for the exponent. You can think of it as unit conversion or whatever. But if I find the number of COVID cases 4 weeks later, you're not going to put a 4 here because that'd be 4 days. We need 4 times 7 or 28 in that spot. Now, one last sort of thing to think about, and this is what we're going to be talking about next week. In terms of that, we devised this based on data for a percent change over 1 day, 76%. Now, this may be not the best example to talk about like longer periods of time because I would hope that it kind of changes and people recover and whatever. But if I kept getting questions from, like, let's say you're the health people, you keep getting questioned by the media about, well, how much is this increasing in a week? What about after 2 weeks, 3 weeks, 4 weeks? And people keep asking about weeks, or you needed to have data on weeks instead of days, which who knows for what reason that might happen. Any thoughts on how I could change the formula so I could make something about, let's see, let me just write this with D for days, so it's easier to keep track. So this is after a certain number of days. what if I wanted to write a formula where there's a number of weeks involved as the input? Or in other words, yeah,
Would you just do, like 975 and then times 1.76 and then it's D over 7? Cause that's 1 week.
yeah, so I don't want D over 7, so something with however many weeks it
Oh,
is,
So would it,
you're close.
would it be D divided by W then?
Yeah, so D and W are related, right? So my number of days and my number of weeks aren't equal. What could I put in here that relates the two of those?
7 on the D. 7D.
Yeah, 7D equals W. The number of days times 7 would give me a number of weeks, is that right?
Would give you 1 week.
7 days is 1 week. But if I have a number of days, like let's say I've got
But shouldn't function of
14
D,
days.
shouldn't function of D go into function of W, so,
14 days is 2 weeks, right?
alright.
So if I were to put in 14 for D, that'd be the same as putting in 2 for W. So what is it like? So if I gave you, oh, it's been 2 weeks, I don't want to put 2 up here because this is expecting a number of days. Yeah.
Would it just be D over 7?
Let's see, D over.
I guess exponent.
Yeah, so D over 7, the number of days divided by 7 would give you a number of weeks. So if I want to put something about W, if I want to be able to plug in a number of weeks, like I want to be able to plug in some number here and get like 2 weeks. So if I wanted to plug in a number here and have it represent the number of cases after 2 weeks, what number would I actually have to have there, regardless of the symbol? If I meant to have 2 weeks, what would I need to have here on this 1.76? 2 weeks is the same as 14 days, so somehow I would need plugging in 2 to come out to make a 14 here. So 2 for W needs to come out for 14 as this exponent. So what do I need in the exponent? Along with a W, something else.
7?
Yeah. So just in terms of this isn't saying 7 weeks is 1 day, but in terms of this relationship here, the number of the number of days divided by 7 gives us a number of weeks. Or the variable, the symbol D, if you can see this, is the same as 7W. Right, this doesn't mean that a day is 7 weeks. This means that the value D and the value W aren't the same. If I have the value of D, I can divide by 7 and get the number of weeks that comes from that. If I have a number of weeks, or if I have a number of days, I can take the number of weeks and multiply by 7 to get that. So I can write this. Another way to think of that, though, that may be less confusing, I think it is, say, well, all right, this is the growth factor for 1 day. If I'm only going to be dealing in weeks and not dealing with days, then I'm not going to be dealing with 1 of these at a time. I'm always going to be dealing with 7 of those at a time. And just in terms of reinterpreting this, 975 times 1.76 to the 7th power, that would be 1 week's worth of growth, whatever that comes out to be. 1.76 to the 7th power is 1 week's worth of growth. Exponent rules again. If I put a W on that, whatever this comes out to, again, that's the same as this expression we have here, 7W power. Multiply those together. But I could work this out as its own number. I don't know what 1.76 to the 7th power is. 1.76 to the 7th power is my... oh, that's not what I want. Oh yeah, it is. It's a huge percentage. So 1.76 to the power of 7. Yeah, it's 52.3. So in 1 week, I've got a huge amount of change. In a day, it's 76% growth. In a week, it's, well, 1 plus 51 point something. It's like, I don't even know what that is. 52, let's see, move the decimal twice. 5,231% growth, or well, 5,131% growth over the one that was already there. Messy numbers. But if I need to substitute in a different unit of time repeatedly, I can convert or think about larger time frame growth factors as opposed to just 1 day or 1 minute or whatever. If I want to convert it to a larger one, I can work that out in advance, and instead of always having these weird expressions like that and trying to think, well, what do I do with the 7? There's a difference of a factor of 7 between days and weeks, and this looks like I'm multiplying the number of weeks by 7, but it's not. It's multiplying the, well, it is, but the number of weeks times 7 gives you the number of days in that many weeks. So it's just a little bit confusing in terms of the wording of it. So I don't really care about the part 3 of that question. There was something else, not those. I thought there's another question. No, oh, there wasn't one on here. I think it's probably in the module 4, investigation 4, which I don't want to get into right now, right at the end of class, but just in terms of these, it's what your syllabus refers to as n-unit growth factors, which is slated for, I think, the beginning of next week. So it's talking about like, so if it's 3% per day, I could find a percent that corresponds to a number of weeks and use that if I wanted to talk about it that way. That's also something that, in terms of compound interest formulas, you can interpret what we were just doing with that compound interest, the number of quarters and converting to years, same sort of thing. Oh, I can find a yearly growth factor. If it's, what was it, 0.75% per quarter, I can work out in advance what percent growth that is per year. And in fact, that's something more bank people financial terminology, it's called an annual percentage rate, that tells you what actually happens over the course of a year to your money if it's a 3% but quarterly compounded interest rate. So that weird setup that they have, just to make it confusing, is honestly the reason. But if you want to figure out the annual growth rate when you're given interest about growth rate over a smaller period of time, we can convert that by doing, mystery things like this. Taking the growth factor and multiplying it together to make multiples of those growth factors, a week's worth of 76% per day growth raised to the power number of weeks. We can just do this that way instead of having to do this conversion with, wait, do I divide days by 7, but days are shorter than weeks? Why don't I multiply by 7? It's a little bit confusing to think about that way. When you write it in terms of growth factors and think about how many of these does it take to make something else, whether it's a greater than 1 or less than 1 sort of proposition, either way should work. But over the weekend, I'm going to put up some additional questions like looking ahead related to section 4.5. 4.4, I already have those up. I have to do some editing on 4.5 because it was worded strangely. This is the page I was looking for. So you see you've got 4.1 to 4.3 homework due tonight. 4.4 is about those multi-unit growth factors and partial unit growth factors and how to use those. Most of the rest of the material in those is repeats of what we've already seen to this point, but I'm going to add in some 4.5, which is, I forget what topic that was. Is it on here? Where's our syllabus? There we go. So, yeah, next week, Tuesday, partial unit growth factors and n unit growth factors. Let's talk about this like weekly versus daily, or minutes versus if I had a day to start with, how I can break down and talk about the growth or decrease over smaller or longer timeframes, which is also, it's unit conversion, but nice to do, and there's a variety of ways to do it. So that's what we're going to be talking about Tuesday. Your assignment up through tonight is most about 1 unit. These multi-unit, like I said, that's the 4.4 that's due next week. But percent change and all that, that's all due tonight. So make sure you work on that. Zoom tutoring hours available. And I did want to point out, I'm going to have a schedule for him posted soon, but our IA, instead of coming here in the morning, since there's not so many of us this early in the morning, he's going to have additional online office hours just like him, and he'll have a schedule trying to fill in some of the gaps around the Zoom online tutoring where there's no instructors available to do that. So he's going to have his own, and you're welcome to visit him there. I'll have a link to that and his schedule later, but it's probably going to be about 4 days a week for an hour here and there trying to fill in some gaps. All right, have a good weekend. If you do have questions, make sure you post them to the forum or email me, and I'll post them there. And I will see you next time.
What have to do with a laptop?
Yes.
Just started this. So unit growth